So thank you all for coming here today. I'm from UEI, and we build hardware for avionics systems. We are a manufacturer and supplier, and they're used in various avionic-based systems, from ground support equipment to simulation systems in the lab, and it's even deployed in health and usage monitoring systems. And we're known for our technology that is both rugged and flexible. We protect your investment with our 10-year obsolescence guarantee and up to a 10-year warranty. Based on our experience with deployed systems, we'll be using our HUMS, or Health and Usage Monitoring System hardware, as an example in this webinar. Over to you, Colin.
Great, thanks. So BG Networks is a company that has a mantra, which is security automated. And we develop automation tools to make it more efficient and lower cost to implement security in embedded devices, IoT systems, systems like UEI hardware. And we have three products. One is a hardening tool, or a tool that adds security features to a device. It is something that leverages the security features in silicon. The background that we have, the folks at my company have, is in embedded systems. And we are very used to leveraging silicon features in embedded processors, such as cryptographic accelerators, secure key storage, secure boot, and so on, to implement the most secure systems that you have. These tools help you do that very easily, and takes a task to implement security from months of work down to just maybe a couple of weeks. We have a automated test environment for security testing. It's a particularly interesting sort of hardware software automation tool in that it works very well with hardware that can't leave a location or is too big. You can actually take our hardware, put it next to the system that you have to pen test or vulnerability test or provide some kind of validation testing in terms of cybersecurity. And it gives you remote access into the system, into our box, which would actually exercise the interfaces and allow a pen tester to remotely go through the testing that they need to do to make sure that there is no security vulnerabilities in your device. Our third product is a real-time attack detection software. It gives you the ability to detect attacks in real time. It runs on the device. It takes a little bit of memory and megahertz on your device. And it's unique in that it can detect 0 days. It has very, very low false alarm rates. And it can scale from small cores like an M-class ARM core up to multi-core A-class devices. We also offer consulting engineering services and have training. You'll get a little bit of a sense of some of the services that we can offer. We're going to be looking at a threat and risk assessment a little bit later in this webinar, which I think will be pretty interesting for you. And that is the kind of, will give you a flavor of the sort of services that we offer.
You know, what we are going to cover today is everything from an introduction to zero trust, and look at some of the 7 NIST tenets, as well as looking at a process for threat and risk assessments. We will review that in the context of an aircraft health and usage monitoring system. And we're going to look at some of the tools and mitigation schemes to reduce some of this cyber risk on this HUM system. And then we're going to look at specifically how to use some of the security controls on the hardware and in the software to actually cyber secure this hardware. And then, of course, we can't forget the key management considerations.
Great. So we'll start off with here kind of a fun exercise to get us warmed up. And it has some, I think, interesting insights also. These are our hack, not hack slides. And the idea behind these slides is I'm asking the question, do you think, in this case, a 2020 Mercedes was hacked or not hacked? We're not going to take any polls or anything. It's just for you to do yourself. And I'll give you a moment. We've got about 5 of these slides, and we'll quickly run through them. So the 2020 Mercedes, hacked or not hacked? Well, in this case, it was hacked. There was a number of vulnerabilities that were found. One of the most egregious was while they had their certificates, essentially their keys to the cloud interface in the vehicles, wrapped, right? So they actually wrap the key, or they wrap the certificate in an encrypted way that's cryptographically secure. They left the key encryption keys, or the certificate encryption keys, in plain text, and the adversaries were able to use those keys, essentially decrypt the certificates, get access to the certificates, and then get access to the cloud and access functionality that was available through the cloud, kind of that remote app functionality of door locks, sunroof, starting the vehicle. Mercedes actually had this research actually funded. So they sponsored the research. It was properly disclosed, and Mercedes has a very good over-the-air update system, kind of a little bit of a validation of how important that is. They were able to roll out fixes to, I think, a couple million vehicles within a matter of days to fix these vulnerabilities found after they were disclosed. So I thought that was an interesting one. The next one here is Apple AirTags. What do you think? Hacked or not hacked? Hacked. In this case, it was a power glitching attack that was used. You can actually see the method and approaches that were used in a DEF CON video. It's on YouTube if you care to look it up. The researchers used timing of bringing up the power on the device so that they actually dropped the power at a very specific point in time in the booting of the Nordic Bluetooth chip that's used or was used in the Apple AirTags, so that when it was actually about to secure the JTAG interface, those instructions were skipped. And so by glitching the power at exactly the right time, they caused the instructions to secure the JTAG to be skipped, which left the JTAG interface on the AirTag devices open. And then they were able to gain full access to the internal memory on the device. And there was no super significant kind of impacts in this case, but they were able to do things like, having an AirTag physically with them and, make, Apple think that the AirTag was, 1,000 miles away. This is a industrial control system. Hacked or not hacked? This one was hacked. This is about 3-4 years ago. It is a oil and gas refinery where this system was located. The adversaries actually got persistence on the system, so they were able to hack the system and maintain their presence on the system. The only way they were found was they tripped a shutdown control twice accidentally, and by the second time that happened, the people running the oil and gas refinery figured out that there was something wrong. In this case, they did not have the security controls turned on in the device. So the lesson learned here is, make sure that, when you're deployed devices, there isn't a way to turn off your security configurations, or you're at least able to tell if the security configurations are turned off. The other thing here is having some kind of ability to determine if the device has been compromised. Kind of a real-time intrusion detection capability would be something that could have indicated that these devices were compromised. And we have one more here. F-35, U.S. fighter aircraft, hacked or not hacked? Well, we tried to trick you. This one is not hacked here. Thank goodness the Department of Defense in the United States does a very good job at cybersecurity, and there's nothing that we know of publicly that these aircraft have ever been compromised. So that was hopefully a little bit interesting, a little bit informative to you, and got us warmed up. And I'll start off here with zero trust as we get into the meat of the presentation. The reason we added a zero trust slide here was, as we were going through the example and preparing for the webinar, we realized that as we were thinking about how to secure a hum system, that naturally these elements, certain of these elements of zero trust were naturally implemented. And what zero trust is to move away from a perimeter security mindset, where you put firewalls at the edge of your network and you assume that everything internally is secure. It's a move away from that. The assumption now with the zero trust mindset is that the network's been compromised, that there is not a trusted relationship or trust assumed with another entity in the network just because they are in the network or they have some kind of physical proximity that you assume to be secure. The assumption is that the devices within the network have been compromised. And so what that leads to is a security architecture where there's microsegmentation, where you have security within certain devices or certain areas of the network. You continually authenticate within the network, you encrypt communications, and then dynamically based on the state of the network, you're actually thinking about access management and whether or not a certain device should have a certain type of access management. A great document for zero trust is the NIST SP 800-207. This is publicly available on the web, on the NIST website. And the 7 tenets here that are listed in SP 800-207, the few that we'll end up talking about here in our simple example is around thinking of data and compute as resources that need to be protected. So you're actually thinking about the data itself as the entity that needs to be protected. That access to resources are granted on an individual session basis. And then access is based on policy. You're really thinking about who's getting access to these devices. What does a risk-based approach mean? Well, a risk-based approach means that you're considering a certain item, you define the boundary, and you'll see here as we define the boundary of UEI hardware and a HUM system that needs to be protected in a certain scenario, that we're defining essentially the UEI hardware that has an embedded processor, it has data acquisition capability, and it's that device that we want to secure because we want to keep the data in that device from falling into adversarial hands. And once you've defined the item, you want to pull together information about the item so that you can consider the possible threats. You may create a data flow diagram. STRIDE is one way to think about the sort of threats that you have. STRIDE stands for spoofing. It stands for tampering, repudiation, information disclosure. This is the specific one we're going to talk about today: denial of service and elevation of privilege. It's one of many threat modeling approaches you can use. We've also used like CIA, confidentiality, integrity, and availability. It's kind of a subset of STRIDE. You could use that. There's other approaches around threat modeling that you can use. It's up to you usually, and the various regulations and standards are out there that typically allow you flexibility in deciding specifically the sort of threat model that you want to use. So you create the threat model, you create the possible sources of threats and what they could impact. In our case, it's going to be data that could be accessed over like an Ethernet interface or an RS-232 interface. You list the threats and you consider the threats to get to a risk rating in 2 ways. One way is the feasibility of the threat happening. And if you look at something like CVSS, which is a very well-known rating for threats, this absolutely considers the feasibility of the threat happening and takes into account things like, are there any special tools the adversary has to have to expose the threat? Do they have to have a certain level of skill? Is the system available for a long period of time so they can try a lot of different things and experiment with the system to find a weakness? These are all things that go into considering the feasibility of an attack. But you also, when you start talking about a physical device, want to consider the impact, not only from a data exposure or financial risk perspective, but you also want to consider it from an operational perspective. And then also if there's a safety risk associated with it. When you start talking about IoT devices or hardware like that UEI has that can have potentially control over a physical device, there is the potential of a safety risk also that you'd want to consider. And you consider both those aspects in terms of the impact and also the attack feasibility. And that can allow you to come up with a risk ranking. You can actually end up with a number, so you can rank your risk from top to bottom. And then you can decide for each one of those risks, how do you want to treat the risk? For the high priority risks, the ones that the adversaries, that you're concerned they could compromise the device, it's feasible that they could cause a compromise. And then also for the impact, like in our case, that the data is sensitive, we want to make sure it's protected. If it got out, that would be a bad thing. You'd want to have a risk treatment. You want to put in some kind of cryptographic control into the device so that you're going to protect against that potential threat from actually becoming a reality. There's other options you have here, like you could decide that to accept the risk, for example. Maybe the risk is low and the chances of it happening are low. The impact of if the risk was exposed, the threat was exposed, is very low. And you might just decide to accept that risk because it's going to be too much work to go and actually implement the security. But this gives you a way to think about that, the whole threat and risk analysis, to decide exactly what kind of security you need in the device, and not putting too much security in and making sure you're not putting too little security in. At a high level, I'd say that is what you're trying to do with a risk-based approach, which is really figure out what is the right amount of security to put into a device. Here is our threat model for the HUM system. The scenario that we came up with for this threat model was an aircraft crashes, the HUMS module is stolen, and then the hackers attempt to access confidential data. That data might be from the various systems, might have been recorded. That might have been, let's say, on a helicopter if it had crashed, for example. And when you look at the UEI hardware, the interfaces that we care about on the hardware are the RS-232 interface, the RJ45, which is an Ethernet interface, and there's also an SD card interface on the device. We're not worried about the USB because those are output-only interfaces on the UEI hardware. And in this little threat analysis that we did, we came up with 6 attack paths. One is through the Ethernet interface, trying to find like an SSH sort of application, try to brute force any passwords. So that would be number 1 here. Number 2 would be using the RS-232, trying to plug in there, maybe finding if there was some kind of telnet interface, again, trying to brute force any passwords that might be on there. Number 3 is similar to number 2 in that, in this case, maybe they physically decompose the device. They actually take the enclosure off the device, they find the UART pins and maybe solder directly to them and try to perform a similar attack. The 4th one is, again, a physical attack where they've actually removed the enclosure, have access to the eMMC memory that's on the device, the flash memory, desolder it from the device. This would be a significant amount of effort. This is not an easy attack to do, but one you certainly want to consider. Put it in a flash chip reader and then try to read out the secure data that would be stored in the file system, in the Linux file system on the device. The 5th one is the SD card. If they put in an SD card device with a malicious payload and then try to get the UEI hardware to mount that code that's in the SD card and then run that code, which would then give them control and access over the device. That's certainly a very obvious and easy path that you want to make sure you consider securing against. And then the final one, again, is one that requires some kind of physical access, which is finding the JTAG pins, soldering to the pins, and then trying to access the device over JTAG, which again would expose fully the memory if there was that sort of access was allowed and permitted. So considering those attack paths, there are 6 mitigations that we've considered here. These aren't the only ones. These are not a full list. It can get complicated quickly. We were talking about it a little bit earlier this morning. For example, if you're considering the static case where the device is not powered, that is really what we're considering here. If they have the device powered and they're trying to attack it, there is dynamic, access that you would need to consider. So, for instance, if the device was somehow put in a mode where it was transmitting data, you'd want to make sure that the data was encrypted over that Ethernet interface, for example. But specifically here for the case that we were considering, attack path 1, you could have a password, or you could do some kind of authentication. There's pros and cons to either approach here, which we'd be happy to talk about. The same with the RS-232 interface. You want to have an authenticated session, potentially a password. For the flash and SSD of solid-state device memory that's in the actual UEI hardware, you'd want to encrypt the data. That's going to protect it if they did take the flash off the board and put it into a chip reader. They wouldn't be able to access the data because it would be encrypted. There's a mistake here. This is not media access control. This is mandatory access control. This is something that would help more if the device was running in real time, and would protect if the adversary was trying to gain access to individual files. So media access control can be a way to have certain files that are protected. And this is something that is in feature in SE Linux, which the UEI hardware supports. In terms of, in a static way, putting in that SD card, resetting the device, having it boot up, and then, if you were trying to protect against that malicious code that's in that SD card interface from being run, there's a secure boot capability in the UEI hardware, and that would prevent that. Secure boot basically will make sure that only code that has been signed and authenticated and is verified, that hasn't been tampered with, is actually going to run in the device. And then the final path here is the JTAG. And this would leverage features that are actually in the processor, in the UEI hardware, where there's a capability to lock the JTAG interface with a password that can't be brute forced. You can put enough characters into the password so it won't be brute forced. The secure boot capability also leverages features that are actually in the embedded processor. And along with the encrypted data, this would leverage a tool that UEI offers, which Erik will be talking about here on the next slide, called UEI SAT. These attack path mitigations would use UEI's secure Linux toolbox. And so there's a couple of offerings that we'll be talking about in a second that would allow you to implement all of the risk mitigations that we have outlined here on the slide. Erik,
thanks.
over to you.
Yeah, thank you, Colin. Goodness, I hope our hardware doesn't come under any of these attacks, but should you want to protect against that, here is an example of securing the root file system. So this would help with something like attack path 5. It would help with the JTAG attack. It would help with encrypting data on the flash, on the SSD, and actually many of those attack paths. So some of the steps that are needed to extend the hardware root of trust, to secure U-boot, to secure the Linux kernel, and to secure any applications on the root file system. First, you would need to use the correct configuration and recipes in a Yocto build to enable the authentication and encryption of the Linux file system. This is conveniently captured in the ESSA Yocto script. Then the engineering team can use the tool, like the security automation tool, to configure the type of encryption and authentication needed. This will be used to encrypt, sign, and lock the various binaries, libraries, and any application that you've coded up that is on the system. After the system is configured, the deployment team can use the tool to apply the configuration to any and all of the hardware. The security automation tool enables embedded engineers to develop cybersecurity code efficiently and effectively without needing a background in cybersecurity, which is good because I am certainly not like Colin. With this tool, engineers can easily improve security capabilities, enhance productivity, and reduce the time required to take advantage of the security features built into the hardware on our platforms. To secure your Linux software using these tools, the starting point is the Enhanced Security Software Architecture, or ESSA. Build your software using the ESSA layer which is Yocto-based. This will result in a bootloader with the IMX security features, which is the hardware, the Linux kernel, and the root file system being encrypted and signed. The next step is to use the security automation tool by answering a series of questions to generate the keys to encrypt and sign U-boot and sign the Linux kernel. The security automation tool is then used to download your code to flash memory, lock the processor, and the interfaces like JTAG and the serial console. If I remember correctly, those were a couple of the scenarios presented, one of which was the JTAG penetration. If the interface is disabled, this would not be possible. You don't even need a password. This will result in code that is stored in an encrypted form in the flash memory, and it will be authenticated and checked for integrity on boot. Well, this will certainly help with anybody trying to put any kind of malicious code onto this system. Since the code is running on the hardware, will be written on top of an OS, we need to ensure we are using a cybersecure version. We use an image based on SE Linux that has the latest patches and enables all administrative control of the password policies, logging, auditing, and the like. This is also used in conjunction with the secure automation tool for the algorithms to support encryption of the data in motion and the data at rest. Any code that is developed to run on the hardware needs to ensure that any data it is logging or sending is encrypted appropriately. Otherwise, there goes your cybersecurity. Using the tools for the software and the hardware can assist in bringing a home system into NIST 800-213 compliance. Part of the compliance is using security requirement guidance. We ensure that our implementation of Linux, the encryption, the authentication, and the tools to bring it all together are compliant to a list of SRGs. We supply a list like these SRGs. What you see here is a small subset of the SRGs that we are supporting that can be applied to generate a security technical implementation guide, or STIG. Your specific implementation may be different, but we supply all the tools so you have all these options available to you. One thing that pulls this all together would be key management, which is another big issue. Right, Colin?
Great, thanks, Eric. And key management is something that we find is commonly overlooked. There could be a lot of effort put in on the engineering side of things to consider threats and consider risks. But I think sometimes it gets overlooked because you need to pull in the manufacturing organization. And it is very important that they understand what they need to do to keep keys secure, your secrets secure, as well as, an engineering team that had followed a very robust and thorough, secure development process framework. And, if you look at what the engineering team would do, like we did earlier, you'd have a threat and risk assessment that you'd look at. You'd figure out the security features from that threat and risk assessment. So like, let's say you were saying secure boot. I'm going to use RSA, digital signatures, authentication. That might be a specific security requirement or a specific security spec that you're going to implement, for example. You would apply those security features and configurations, leverage, like I had talked about before, ideally the hardware that the chip has, and go through your testing and validation. So you go through the steps over here on the left, you end up with a software stack that has code that is signed, code that has been encrypted, and you've actually got keys stored, either in the device or externally. You have this concept of certain keys can be public, anybody can see them. Certain keys that are private, those are the ones that you need to make sure remain secret. And then you have to communicate that to the manufacturing team and help them in terms of, how do they go about generating keys? How do they go about signing the firmware? How do they go about encrypting the firmware, downloading the keys that they need to download to the device, and then downloading the security or the secured firmware down to the device, and then making sure that the device is actually put into a secure mode. So the manufacturing team needs to understand how those cryptographic operations are done, or they need to be given kind of a way or a method so that they don't have to dive into the details of those things, so that keys can be generated, keys can be used to sign, to encrypt, and then the keys are managed correctly, either downloaded to the device or storing securely in the manufacturing environment. And some considerations for this, we've talked a little bit about this already, that you need to consider manufacturing. From an engineering side of things, you want to consider code signing and release procedures. Who has access to code signing? Who has access to those keys? You want to make sure, ideally, that there's limited number of people who have access to that. You want to try to automate that as much as possible, if you can, so that the process is repeatable and doesn't have mistakes in it. Ideally, we'll talk about this in a minute, if you can keep the keys within the cryptographic boundary, and you saw the boundary that we defined in the HUMS example, which is the UEI hardware, and specifically in the UEI hardware in the embedded processor, the IMX 6 processor that's from NXP, that is going to save you on the key management. It avoids having keys offline or keys that are outside the device, if you can leverage that. But you certainly will need to have capability to store keys somewhere securely in your manufacturing environment. You could use a hardware security module. You could also use cloud-based storage, which is pretty common today. And for instance, Amazon Web Services, they actually have HSMs in the cloud that you can leverage that can securely secure your keys. If you look at key management very specifically in kind of a production environment, you want to protect your keys, because your keys are the secret. The algorithm that you use is not the secret. So AES, which is a symmetric encryption standard, is public. It's known. RSA, DSA, which I mentioned before, which you could use for secure boot, for authenticating and making sure that the code that is run on startup has authenticity, you know where it came from, it has integrity. The RSA algorithm, that's known. What makes your code secret, what keeps it secret, it's the keys. So the burden is on the keys, so you want to make sure that you protect your keys. There's a standard in the US called NIST 800-171, which is similar to 800-53. These are IT level security processes, and you want to leverage those standards. Those are two that you could leverage in terms of coming up with the right controls around keeping your keys secure. Things you want to consider are storing your keys in actual hardware, or making sure they're stored securely with the engineering team, if that's the method you're going to choose. Physical controls, you would have considered the possible risks and mitigated those risks in terms of somebody maybe in the manufacturing team getting access to those keys, and if they in a situation where they shouldn't have access, you want to make sure procedures are followed and confirm that they are, in terms of keeping those secrets, those keys secret, and then make sure that you're backing those things up. And one of the challenges with embedded systems is there's a lot of keys. So in the example that we just talked about, the HUM system and those mitigations that we talked about, where you'd have secure boot, it boots U-boot, it boots the Linux kernel, it boots the Linux OS. There's different stages of authentication that goes on. And then if you want to have encrypted communications, if you want to encrypt the root file system and make sure that the key isn't stored in plain text like it was in that Mercedes example, you'd want to have keys that are on the device and they are stored securely in the device. And this is the reason where, as you start considering all these things, why there isn't just one certificate in an embedded system. You actually have many sorts of keys. And so this is an example here of the keys that you would have for those risk mitigations that we talked about, in our example earlier here. So it's just not one. You see there's probably about 10 or 12 here that you need to consider. The ones in red are the private keys. These are the ones that you need to make sure are secure. There's one here that actually gets flashed into the device in the UI hardware, the NXP processor. And then others here would be stored securely in the secure key storage capabilities and features that are in the embedded processor. And here's an example, or here's the diagram, I should say, of the security features that are in that embedded processor, including the ability to store keys securely in this secure key module in this cryptographic accelerator that's on this NXP processor. Keys can be programmed into a device, or they can be generated. In the case of NXP, one of the things we take advantage of is they actually program a key into the device. It's unique, and it can be used for the encrypting of the file system. It's what we actually use as the basis to keep the encryption of the file system secure, to keep that key secure, so that in this design, if you tried to look for the key that we use to encrypt that file system, it's not available. It's not in plain text. It's actually stored securely, in the CAM here. You also have an option of wrapping keys too, which is something that this NXP processor supports. So if you're not storing it within this hardware, you actually use what's called the key encryption key to actually encrypt the key that you're going to use to decrypt the root file system. And that's actually the method. It's there's multiple steps associated with this, but that we're using. So you actually have a key blob that's stored in the memory on the device. It's encrypted. You have to decrypt that key blob actually in this CAM hardware unit to gain access to the key and then be able to decrypt the root file system. And the benefit of on-chip keys is you don't need to generate it. You don't need to store it in some kind of external hardware security module device, and it's not exposed in the manufacturing environment. I'll turn it over to you, Erik.
Well, thank you, Colin. So to properly secure your system from intrusion, from reverse engineering, from untrusted code execution, or from bad actors who want to download and discover your secrets, we typically break this up into three aspects. One is securely boot your device, extend the root of trust so only the code you want is loaded and executed. This would certainly help out with PAS 5, when the actor wanted to try and boot off an SD card, some of their SD card, or even on Path 4, where they are trying to look at your flash and your SSD. You should always use a secure OS and make sure your application is using any kind of encryption that is enacted by that Linux OS. You want to ensure that you have administrative control over your entire system, and you're using the correct encryption algorithms for data stored or transmitted. This would certainly help with any data at rest that's stored on your flash or your SSD, which is, I think that was Path 4 in our attack path. And then the third thing would be to secure your hardware. You want to deactivate any hardware interfaces that are not needed. Extra serial ports, JTAG interfaces, another Ethernet port, and of course, turn off that USB port. This would help with PAS 2, 3, and 6, so that any bad actors will not even have access to any of those interfaces. All this is supported using the security automation tool and the hardware resident. And of course, if you need help, our partner BG Networks are experts that can provide embedded security training. They can assist in your code development. They have tools to detect attacks and even test your systems. And of course, we cannot forget the key management tools. Do you have anything to add, Colin?
No, I think that's it, Erik. Thank you.
Wow, how time flies. So thank you. And I would love to open it up to any questions.
Thanks, guys. Really interesting presentation there. I thoroughly enjoyed that. Learned a lot there. I'll jump straight into the questions here. We've got a couple here from Garth Stevenson. We've got about 15 minutes here. So if anybody watching does have any questions, now would be a great time to ask them, because we often do run out of time. So Garth is asking here, How does your supply chain security work? Does it include HBOM or SBOM chain of custody? If so, in what format?
Well, thanks, Garv. That's a great question. I am not the correct person to ask that kind of question because I don't deal with the physical operations. I don't deal with manufacturing or part sourcing here at UEI. I do know that, yes, we have to take all that into account in order to have a secure ecosystem here at UEI to build these secure products.
Yeah, Erik, I'll add on the SBOM side. It's a great question. So from an SBOM standpoint, and this is something that has had a lot of visibility recently, over the last couple of years, and it was really, I think it was the SolarWinds attack where there was some compromises of software that, it came from a trusted source at the end of the day. They compromised some of the signing systems at SolarWinds, but it really brought a focus to SBOMs. And what SBOMs means, software bill of materials, is that where your software is coming from. It's from an authentic source. That the software has not been tampered with. If you write all your code from scratch, you're in good shape, right? Because you know the source, the provenance of that code. If you're buying code from somebody like UEI, for example, you want to make sure that it's a trusted partner, which UEI is. If you're using open source, you really need to check, especially. And we've got a tool that it's a free to use tool. We put it up on GitHub, where you can actually take advantage of some of the revision tracking capabilities that Linux has. And what this tool does, and we can share the link here in a minute, would actually go and check at the different versions of packages that you have used in your Linux build. It will then go and take advantage of a really cool open source project from a group called OWASP. OWASP is a group that community that provides kind of free help, free ideas, free information, and free code for security, and it's called Dependency Track. And so our tool will generate a Cyclone DX format SBOM. It will then automatically send it up to Dependency Track for you. And then Dependency Track is going to check multiple times per day the NIST vulnerability database. The NIST vulnerability database, NVD, is one of the premier sources to know if some kind of code has been compromised and somebody has reported a code being compromised, some sort of open source. And then if it does find that something is reported, it's actually going to send you an email or give you a warning that you have a vulnerability in your code. So a little background on SBOMs, and we have a little bit of help there for your Linux stack in terms of tracking SBOMs and making sure there isn't a vulnerability there.
Great, thanks, Colin. Let's take this other question from Garv as well. He also would like to know that if, aside from secure boot and soft TPMs, trust zones, are there any other UP chip level requirements needed to support the security automation tool here?
Well, that's another great question. When we talk specifically about UEI hardware, we certainly can use a hard TPM chip for key management, as well as we use all the resources we can on the chipsets available.
Right. Anything to add there, Colin?
Yeah, sure, absolutely. So what we're leveraging in the silicon there is secure boot to start. That's actually built into the silicon. They have NXP puts ROM code into the device, which is secure boot code. They've architected it in a way that it is only going to look at code that you specify it to look at. In terms of if you decide to look at internal code on the device, or if you want to boot externally, you can set that configuration. And then it's going to check for authenticity of the code that's about to be run. and it's going to check to make sure it hasn't been tampered with. And it uses, I mentioned that RSA algorithm that gives you both, authenticity and integrity. It checks both of those when you actually do this. And then it is going to use the key that it uses is you actually have a key, a public key that is appended to the end of your file. And then there's a hash that's actually burnt into the OTP on the device. And it actually uses that hash to verify that the key is correct. Then once it has the public key, you can go ahead and do the check for authenticity and for integrity on the device. So that's one feature. Another feature that we use is that secure key storage on the device. That's important if you don't want to have keys in plain text. Another is the crypto accelerators. So there's AES accelerators on there. There's asymmetric accelerators that are on the device. There's also random number generators, which you need if you need to generate keys for sessions in real time. And there's other security features that you'd see, like trust zone. We're not using trust zone in this case, but those are the main features that we're using. I'd say is the secure boot, the crypto accelerators, the random number generators, and the secure key storage on the device. Those are your kind of basic tools. And in a lot of cases, you'll string those different tools together to come up with something like having a wrapped key, a key blob, to make sure that your Linux root file system has been encrypted properly and the key is not accessible.
Great, thanks, Colin. Got some more questions here, which is great, and a statement here from Lara, who's found the webinar quite useful, which is great to know. Thanks, Lara. And this person here is simply known as Bob. So Bob would like to know if some processes are more or less secure than others. You want to take a stab at that?
Well, I can say from a UEI perspective, certainly, because we basically support three different types: PowerPC, ARM, and Intel. And we're using a lot of the on-chip resources from the ARM-based IMXs, which the PowerPCs simply don't have. So it would take a little bit more to lock those PowerPC systems down. Mm-hmm. As far as Colin's knowledge, I'm sure he knows a lot more.
Yeah, and absolutely, there are differences, and Erik is touching on an important one. The older processors, the more legacy processors, don't have typically very good security in them. It wasn't something that most vendors had thought about previously as needing. But I would say most of the processors out there now are doing a good job with security. The semiconductor industry, the processor companies have done a good job of adding security, and the sort of things that you'll look for, are the sort of things that I've been talking about here. A hardware security module, the term's a little bit overloaded, but an HSM can be that box externally that is used to store keys in a manufacturing environment. Some people refer to an HSM or a hardware security element, an HSE, that would be on the device. And it's what we showed in a previous slide here. The IMX6 actually has very good security because NXP has been doing security for a long time, and they've been doing a very, very good job at implementing security. And in there, you'll have those cryptographic accelerators. You'll have some secure memory usually. You'll have that secure key storage that I talked about earlier. They also have a nice feature, which is called an SNVS, where if secure boot fails, and it fails multiple times, you can configure it so it will actually stop continuing to boot. The assumption is that somebody's tampering with the device. It can actually even look at, GPIO also, that if you want to have some kind of check to see if somebody removes the cover off the device, this SNVS has got a power backup. So even if power is not stored on the device or isn't active on the device and running, it can still check for these things. So yeah, there are differences. You should, if you're considering a new processor type, you definitely want to take a look. But in this hardware with IMX6 from NXP, we've got all the security features that we need. And the thing with leveraging this security in silicon is it gives you the most secure way to do things. Like I talked about before, you can store keys securely, as opposed to that 2020 Mercedes where they had keys, sensitive materials actually stored in plain text, and the attackers were able to take advantage of that. And then it also gives you power advantages, efficiency advantages. Those crypto accelerators are going to run very fast. If you're trying to implement things only in software, you could end up running slower if you weren't taking advantage of those accelerators, for example.
Right. So the more modern, the better. Really, is that the message? Or
you pretty much, you still have to look, Ben. You still have to look to make sure. Yeah. But the modern processors, pretty much all the vendors now know that they need to add cybersecurity.
Great. Okay. Thanks. We got there's a question here. But it's a request really for the link to the free tool that checks for the NIST vulnerabilities. I don't know if maybe you can stick that as a sticky message. Put that in as a sticky message, Colin.
Yeah. No, I'll do that right now.
Yeah. Okay. Cool. I've got a couple of questions myself here, actually. I don't know what level everyone's in at with the cybersecurity stuff, but I'm pretty fresh in. So, I mean, what does FIPS encryption mean? Could someone tell me that?
You want to take that, Colin?
I don't know if you can do two things at once. Yeah.
Colin? Yeah. Exactly. That's what I'll try to do here. Is FIPS encryption is a standard from NIST, and it basically specifies the way that you implement these cryptographic standards. And it says you have to make sure it's done this way to ensure that you haven't implemented with some kind of weakness, and you actually go get certified. So if you have hardware that is FIPS certified, if you have hardware that or software that's FIPS certified, it means that in a nutshell, that cryptography has been implemented correctly. Now, FIPS also gives you layers of certification where you can go to further layers up. Not only has your cryptography been implemented correctly, but that you've put additional layers, physical layers of security into the device. So, for instance, if the device has been tampered with, you erase the keys. That's something that is a higher level of FIPS certification. And you can get, I think there's 4 levels, from level 1 to level 4 in terms of certification. So FIPS tells you cryptographically things are done correctly. And it also gives you an idea of how much security has been put in the device. Not only kind of security in terms of encryption, but also physical security too.
Okay, great. Thanks, Colin. Let's ask a UEI one.
And I was just about to add, we certainly supply FIPS certified algorithms, but they only work if they are implemented, if somebody actually uses them within their applications, because they can very easily write an application that doesn't write encrypted or log encrypted data, does not send encrypted messages. So all this is good, but you have to use the tools.
Okay, great. Thanks. Thanks there, Erik. I do have another one here from people watching. Someone called Christopher Sundberg. Man, this sounds complex. How is post-quantum cryptography impacting some of these layers? Are the quantum-resistant algorithms ready to go into data hardware? You want to take that one, Erik?
I don't know much about quantum cryptography at this point, and it's. I can tell you one thing is we certainly don't have that on our hardware yet. So,
Colin,
I can comment. Yeah, so quantum computers can break asymmetric encryption when they become available. There's something called Schroer's algorithm. Is very good at factoring prime numbers. Your asymmetric cryptography is based on prime number factorization. So RSA, for example, will become insecure at some point in the future. Now, it's hard to tell when. When is a quantum computer available? When is a quantum computer available to your adversary? When will it be low enough cost that your adversary is going to take an expensive quantum computer to actually use it to try to break the cryptography that you might have, let's say in the Hums example? Would your adversary take a $50 million, $100 million quantum computer and dedicate it to, breaking the cryptography that could be in your hum system, for example. They might not. The data just might not be that valuable to them to go and do that. But the financial institutions out there need to consider this, because there's a huge financial risk. You're seeing them going off and, putting in provisions for quantum resistant algorithms. Your AES, your symmetric algorithms, they're fine. They're not exposed to this kind of threat that quantum computers have to asymmetric algorithms. I have not seen in any embedded processors yet quantum accelerators implemented. So that is something that hasn't been done. That's something that you'd have to go off and figure out in run it in software in the IMX processor. I think it would be pretty heavy to run. I don't have benchmarks for that. But if you did want to make or implement quantum resistant asymmetric algorithms, you'd need to think about some, I'd say it wouldn't be low cost hardware. You'd need something that was much heavier to be able to do that. There's a number of companies out there that offer it that you can go and check on. They're developing the algorithms. The standards process, at least in the United States, is in kind of full stream right now, or it's ongoing. There has been some preliminary standards decided, but there's still some time needed to actually fully standardize on what are going to be the quantum algorithms used going forward in the future.
Great. Okay. Thanks for that, Colin. That kind of brings us up to time, guys. So I'll close the webinar in just a moment. I've added the link there to the UEI security automation tool. I've really enjoyed this. It's been very interesting. I got a whole bunch of, I suppose, dumb questions here that I didn't get to ask. So maybe we'll take them up and maybe do an article in the mag or something. But have you got any last comments, Erik, Colin?
I don't. I want to thank everybody's time today, and this is certainly quite a burgeoning concept that to lock everything down and ensure that there are no holes. So,
yeah,
it's great. Thank you. I'd like to thank everybody too.
Great. Yeah, thanks for your attention, everybody. It's we appreciate you turning in and posing such great questions to the presenters here. It's great to see the level of engagement and interest in this topic.